So let's continue our discussion about our linear model. So last time, we just a very brief recap on Monday, we talked about inference of this coefficient of our interest beta. So one thing we should know that is we have first introduced using the t-test to test each coefficient j, beta j, which is the effect of coefficient or the effect of feature j or predictor j. So t-test is for one element of beta. But if we're interested in more than one element of beta, so we first introduce this wall test, which can help us decide whether a subvector of our beta is zero. And besides the wall test, we also introduced likelihood ratio test. So likelihood ratio test is a more general approach in that it can be applied to other models, not just linear models, but it requires the models to be nested. And also it has some requirement about like the null hypothesis specific parameter space for the parameter versus the alternative. So we also need a space to satisfy some conditions. So for example, you don't want the null hypothesis to be a boundary of a space. And that condition is often called the regularity condition. So we derive the likelihood ratio test, and we show that basically this negative log of this likelihood ratio for linear model can just be constructed based on the RSS, residual sum square, under the null model, which is bigger. It should be bigger than the RSS under the full model, because for the full model, you have more predictors, and you're expected to have smaller residuals in magnitude. And for the denominator, which should be an estimate of our sigma square, the error term variance, and then the error term variance. And last time we explained why we use the full model as our basis for estimating sigma square instead of the reduced model. And the rationale is that we believe in this whole framework that the full model is the true model. And we're wondering whether under this true model, certain coefficients are zero. Okay, so one question following what we said, one question I hope you can think about is we have two strategies, and which strategy is more reasonable or their relative advantages. So suppose that I am interested in testing this. So let me see, the question is, okay, if I am interested in this beta vector, again, I can write it out as beta 0, beta 1 to beta p minus 1. So the first one corresponds to intercept, and the second to last one correspond to the coefficients. So the question is, if I'm interested in, maybe I just write it as beta 0 and maybe beta, how to say, beta 1 to p minus 1. Okay, so I just write it in this way. So then this part, the coefficients, they are p minus 1 dimensional. So the question I'm interested in is, are all p minus 1 coefficients zeros? So if this is my question, then there are two ways to formulate this into a testing problem. I'm laying out the two options. Option one is that we can have the null hypothesis just set as beta 1 to p minus 1. This subvector is a zero vector, and this zero vector has dimensions p minus 1. That's one way. The second way is that I can set up multiple null hypotheses, one for each coefficient. So how about I have H01 as beta 1 being 0, 2 H0 p minus 1 as beta p minus 1 equals to 0. So if I do it this way, then I would have p minus 1 hypothesis, null hypotheses I will have that. While for the top one, I will only have one null hypothesis. Okay, and you may wonder which approach is more advantageous, because basically, if I use option 2, and if my decision is to reject any of these null hypotheses, then it is equivalent, it should be equivalent to reject this option 1's null hypothesis, right? Because their equivalence is that only when these p-1 null hypotheses hold simultaneously, then this option 1's null should hold. Then which one is more advantageous? So statistically, we actually give these two strategies a different name. So this one null hypothesis approach is often called, let me put it here, global null, which means that we specify all coefficients to be 0, while the bottom one is often called individual, just one L, null. So they are named differently. So I'll just quickly say that while both options are available, your decision will depend on the question you want to ask. So something we haven't introduced in this class, but I think is something very important to know in practice, is the so-called multiple testing correction. Okay, so what does this mean? And this means that in the second option, we have multiple statistical tests to do. And suppose that we have p-1 tests, right? And if you are interested in just setting the significance level as 0.05 for each test, then you would have type 1 error of each test, test J, which is defined as the probability of reject H0J given that H0J holds, right? Given that it is true null hypothesis, we reject it. That's your type 1 error. So if you set this to be 0.05, for example, then you would expect how many type 1 errors? So the expected number of false rejections would be similar depending on how many of your tests here are true. But let's just say that maybe, let me just give you a name. Maybe C, say C is the percentage of H0Js that are true. Suppose that I know this, but even though I don't, okay, C times p-1 times 5% is your expected number of false rejections. And you can see that this number will go up as your p goes up. So that's the motivation why people want to do some multiple testing correction, so that this number of false rejections won't be too large. Because you can just see that controlling type 1 error of each test is not enough to control the total number of false rejections, because it depends on p, the number of tests, p-1. So therefore, for people doing the multiple testing correction, one idea is to control this probability that we have at least one false rejection. Okay. And if you want to control this, as long as we make one false rejection, we are unhappy, and we want to control this probability to be very low. And this can be written as this probability of a union of sets J go from 1 to p-1. That is, H0J is a false rejection. We reject this null by mistake. So this union means as long as we have this one of these p-1 events that happen, then we have one false rejection. And here, a typical strategy technique used in probabilities that you can bound this probability of a union of sets by the sum of the probabilities of the sets. So this is a loose bound, but it's very easy to use, has no requirement. That is, you can just take the sum j from 1 to p minus 1 of the probability p that h0j is a false rejection. Okay, and we know this probability is actually our significance level, 0.05. Okay, so you can see that this is actually p minus 1 times 0.05. So, or significance level. So you can see that maybe I should maybe change this to alpha to be more general. And this should be alpha. So yeah, see, this increases with alpha. And here I'll use alpha. So then you can see that if I want to control this probability of making at least one false rejection to be very small. So to control this probability of at least one false rejection, say to be under some Q, maybe I still want to have 5%, for example, then it tells us that alpha less or equal than Q over P minus 1 is sufficient to guarantee the control. So the logic is that if we set our significance level to be very, very small, then we can control this probability of making at least one false rejection. And this is called Bonferroni correction. And this has no requirement on how these tests, so here it has nothing to do with how these different tests are related. Because there's one possibility that our coefficients, because the coefficients are the effects of our predictors, there's possibility that our predictors are correlated or strongly correlated. So you can imagine in the extreme scenario that all the predictors are equal. Basically, they're one thing. If they're all equal, then no wonder that their coefficients should also be equal, right? In that case, if one of them is 0, they should all be 0, and that reduces to option 1, global null. So this Bonferroni correction is something we need if we want to control this at least one false rejection probability. But you can see that this is super conservative. Say if you have P large, like I'll just say 100, then Q 0.05, then alpha will be 0.00005, right? So you will need to add 2 zeros before the 5. So that's a small alpha level for making rejections. Maybe you won't have p-values that small, then you may not make any rejections. So this shows the disadvantage of option 2, because if you have to do this multiple testing correction, you will lose power, right? You are putting so many things together. So this one, I'll just say that conservative power loss. So when we say we lose power, it means that we don't discover anything. We don't reject any null hypotheses, meaning that we don't think any predictors have effects. So I just want to say a little bit, but I would say this is not the focus of this class, so I won't go in depth. So besides Bonferroni correction, there's another criteria which is called the false discovery rate. So it's different from this criteria of at least one false rejection probability. The false discovery rate is defined as expectation of number of false rejections over number of rejections. So we are still allowing the number of false rejections to be larger than 1 or even big number, but we just want to make sure that out of all the rejections, the proportion is small enough. Okay, so this is a different criteria. And if you want to control false discovery rate into Q, typically like Q 5%, typically your corresponding p-value threshold is not as small as this Q over p minus 1. So this one is actually in the middle. So this is like between Bonferroni correction and no correction. So this one, directly using 5% as the threshold, p-value threshold is no correction in terms of conservativeness. Okay. So still, if you do for false discovery correction, you would have a p-value threshold that's less than 0.05. So this FDR, false discovery, was a concept proposed by two statisticians, Benjamini and Hochberg in their 1995 paper. And so that's why this Benjamin-Hochberg procedure, or short as BH procedure, is a way to help you find p-value threshold, a p-value threshold given Q, given the target FDR. But this will require you to input the p-values for these tests. So here we will need p-values ordered from the smallest to largest, but I'll just say that P1 less or equal than P minus 1, because we have P minus 1 tests. So then what Benjamin-Hochberg procedure does is that it's actually, if you use illustration, it's actually pretty straightforward to see how it works. So say that basically you have Q set here, say 5%, for example, and what you have is that you have the order p-values, right? P1 and P2, P minus 1. So you just plot these p-values. And what you compare against is this slope, this line. So this line is basically what? It is basically, this line is Q over the total P minus 1 times, okay, I'll put the middle one, I call PM times M. So for the mth smallest p-value, we compare this with this change in threshold. So the threshold will be bigger for larger p-values. So basically, we compare p-value smallest one versus Q over P minus 1 times 1. And we compare the second smallest p-value with Q over P minus 1 times 2. And we compare the mth p-value versus Q over P minus 1 times M, and so on. So that's why this line I'm drawing here is the change in threshold. And we will see where our p-value is located. So basically, we hope the p-value is below the line, and until the first time it reaches this line, we stop here, and we reject all these p-values before the threshold. That's it. So basically, we check if the mth p-value is less or equal than Q divided by P minus 1 times M until it breaks. Okay, and then reject all the p-values before the break and satisfying the inequalities. So that's the procedure. So in this case, you can see compared to the Bonferroni correction, it is obvious that here the p-value threshold is not as stringent. because you are not comparing all p-values to this small value, but you are comparing p-values based on their order. And the larger the order, the larger the threshold. So we're not going to cover the theory of this FDR control by this procedure, but just coming back to my original purpose of talking about this issue is that we should have this impression that doing multiple testing, there's a price to pay. The price we pay is that we lose power because of the correction. And if your goal is just to check this global null, that is, do any of my predictors have any effects, then you should go with option 1 because it's just one test and you don't need to do multiple testing correction. But nothing is free, right? Going with option 1, it means that you lose the information about individual predictors. So even though you reject the null, global null, you won't know which are the predictors that really have an effect. You don't know that. You lose that information. You just say, oh, I reject my null. So that's why in statistics, there's another strategy that's like a hybrid, which is you do it sequentially. You first check the global null. If you reject it, and then maybe you can go with individual null. Yeah, there's a hand up.
Yeah, just is it also possible to like kind of construct the like 95 confidence interval with like differently like corrected p-values
Of
like bump?
course. Yeah, it's so basically for Bonferroni correction, it is equivalent. So when you adjust, so some people are say doing this. So they actually stick with the, how to say, they stick with the significance level to be 5%, but they multiply each p-value by the number of tests. So you are enlarging your p-value, and then you compare the magnified or enlarged p-values to this alpha. That's another way. An equivalent to that is when you construct confidence interval, right? You multiply the interval length by the number of tests. So in that sense, you're getting very, very wide interval, but the conclusion will be the same. So if you have super wide confidence intervals, they will cover 0 and you won't call them discoveries, right?
Yeah, but for me it sounds quite like straightforward for Bonferroni correction, but like for me like Benjamini
Uh-huh.
Horschberg procedure, like it seems like um I don't know how to like construct like a 95 confidence interval with this approach. So like
Mhm.
yeah.
So people can still do adjusted p-value. So yeah, I think you made a good point. If you really want to do it, then well, I think the straightforward approach is that you find the corresponding p-value threshold for each order p-value and use that threshold as its significance level and go from there. Yeah.
Thank
Yeah.
you.
Thank you. Yeah. All right. So yeah, I think that's my discussion about these two options. They have relative advantages and disadvantages. You get more individual predictive information with option 2. But if you are interested in controlling the global null, then if you use option 2, you will lose some power. While for option 1, you have the best power if you are interested in testing global null. But if you reject it, you still don't know which predictors have effects. Okay. All right, so that's one thing. And then if we continue today, we will introduce ANOVA. It's called analysis of variance. Okay, and just as wall test and likelihood ratio test, ANOVA will be our third approach for you to test if an element or a subvector of beta is 0. So just to quickly say a few things about what ANOVA is basically like. So it is a decomposition of the variance you observe in your response. So that's what it is in essence. Decomposition of observed variance in response. And our response is written as y, right? So recall that our y is this vector y1 to yn n-dimensional vector. Okay, And suppose that we have predicted values of y's based on our linear model, and we call them y hat. Y hat vector y1 hat to yn hat. All right. And then what is each yi hat? As a quick review, so where yi hat can be written as xi transpose beta hat, right? So this xi transpose is the ith row of our design matrix X, and beta hat is the OLS estimate of our beta. Okay, that's the setup. So one thing I want to say is a very, very important property. That is a key property of our linear model. That is, if you take the average of your y's, it will be the same as the average of y hats. So this is the average. It's actually equal to the average of yi hats. And how can we derive this? This actually directly follows from the OLS solution in matrix form. All right. So remember that the proof is actually straightforward if we have that matrix form. That is, we have y hat equal to x beta hat. X is the design matrix, which is equal to, I'll just plug in the formula, OLS formula for beta hat, x times x transpose x inverse x transpose y. So this is my beta hat, right? So you see with this, if I multiply x transpose to both sides, I will get x transpose y hat equals x transpose x transpose x inverse x transpose y. All right, and I will have a cancellation here. So what this tells me is that x transpose y hat equals x transpose y. And then what is x transpose? And what is x? If you recall, x has the first column corresponding to our intercept as ones, right? And then we have x 1 to p minus 1 as the p minus 1 predictors. So if you do that, then x transpose will have the first row as all ones, okay? So what this means is if I just write x transpose as maybe, let me think about a good way to write it. So I'll just write it as, how do you say? I'm thinking about notation because I use xi transpose here already. I'll just say xj transpose here, and j goes from 1 to, I'll say j goes from 0, 1 to p minus 1. Okay, I have p, so xj transpose is p by n. I have p rows. So in other words, this is equivalent to say that xj transpose times y hat equals to xj transpose times y for all j goes from 0, 1 to p minus 1. So basically, in this matrix matrix multiplication, I would have every row of x transpose multiplied by this column vector y hat, right? So that would be equal to every row here multiplied by y. So specifically for j equals 0, it is a row vector of 1s multiplied by y hat equals to a row vector of 1s multiplied by y, right? And what this tells me, this is exactly summation of yi hat equals to summation of yi. So this is a direct result based on this OLS definition. Okay, and with this, which means that they have the same average, I could just call this common average as y bar. Okay, and this is very, very important for my ANOVA because basically what this says is if I want to decompose the total, okay, so basically if I want to decompose the total variance of y, right? What is that? So you may know that it's written as yi minus y bar square I from 1 to n, and I can have dividing n minus 1 here just to be unbiased. That's the variance in my y. And how about the variance in my y hat? Y hat, same formula. Y hat I, because it has the same average as y bar, I'll just write y bar here. Okay. So the ANOVA is about this. So this, I call this 1, I call this 2. ANOVA is basically decomposing 1 as 2 plus something. So this is the variance in our predicted values. And this is the variance in our total, in our observed response. All right. What's their difference? Any ideas? So if I just drop this common 1 over n minus 1, because it's just same thing for both terms, I just drop that constant, just related to sample size. I only work with the two sums. I can actually show that summation yi minus y bar square, and from 1 to n, is equal to summation I from 1 to n yi hat minus y bar square. And the remainder, if we do algebra, we open it up and we do the calculation, it is actually I from 1 to n yi minus yi hat square. In other words, this third term is just the sum of residual squares, because we remember that we call each one ei, the residual. We have that. Okay, so I think I can leave this for you to try to see whether you can derive it. But just to make sure that to do it, you may want to use this formula to make it easier for you. What is y hat, right? You go back to beta hat and you can then go back to y. So then you can see why this is the case. And actually, maybe you can actually go simpler with that because we have y hat I in both terms. So if you open it up, you will have yi square, yi hat square, and cross terms yi and yi hat here when you open it up. And here you would just have yi square and yi cross with y bar. And you have yi hat square, yi hat cross with y bar. So basically, if you go back to the definition of y bar, you can open it up. Yeah, you don't need to go back to the definition of y hat to prove this. All right, so this is very good interpretation because we can give each term a name. So this is called SST, which stands for sum of squares total. That's why I call it total variance. And this is called SSR, sum of squares regression. R stands for regression. Why is that? The reason is because we're using a regression model to predict our y, and we're using the predicted values instead of the original values to do the calculation. So we're using a model fitted value instead of the raw value total variance. And the third term is called SSE, sum of squares error. Okay, and this one has another name, RSS, we have seen, right? Residual sum of squares. So this terminology might be confusing, but in the context of ANOVA, we use SSE just to be, more consistent with SST and SSR. So for SSE, it means the error that our model cannot explain. So basically, this is our model part. And this is our residual part. And this is our data. So we start from our data and we decompose the variance in our data into what can be explained by the model and what cannot, and the residual. Okay. So basically, when we have the ANOVA, another thing we can think about is what if we have no predictors at all? And that's what we call baseline model or null model. Baseline model, or you can call it null model. That is no predictors, no covariance, only intercept. So in that case, how would you write down such a model? Because this is the case when no predictors are included, and if we just think about our likelihood ratio test or the wall test for this scenario we just discussed, right? If we're interested in testing all these p-1 effects to be 0, and there's only one intercept left, then how do we write down this model? This model is essentially yi equals beta 0 intercept plus epsilon I. That's it. So there's no predictor included. Okay, and we have, if we still want to be consistent with our assumption, we can assume epsilon I to be normally distributed with 0 mean, common mean, sigma squared. So this is one extreme. All predictors are gone. And the second extreme is, another extreme is the so-called saturated model. I'm just introducing the terminologies so that we can use them later. Saturated model is what? It's basically you have one, one parameter, one expected value per response. So in this case, you have number of parameters mu1 to mu(n) equal to number of observations y1 to yn. So in this saturated model, let me just write it further. We can write it as yi as equal to mu I plus epsilon I. So here, each yi has its own mu I. So as I go from 1 to n, so every yi basically is independent of each other, right? So or I would say not independent of each other because we know why are independent because of this randomness. But here what I'm trying to say is that here the yi's, they can have very, very different meanings. In other words, their mu i's have no relationship. So previously in the linear model, you can see, I'll just grab another paper. So if you think about linear model, if we write it this way, so here we have p parameters, and p in the classical setting is less than n observations. So we have more observations than our parameters, right? So in this case, in the linear model, if I still use the same format to write down my yi, what is it? It's actually yi equals to xi transpose beta plus epsilon I. This is what we just saw. And again, if we assume the same assumption, epsilon I, and that gave us 3 models. So you can see that in this model, basically, even though different yi's, their mean is xi transpose beta, have difference in xi transpose, or they are different in their predictor values or covariates, but they share the same common beta. And that sharing means that we tie them together, right? This model is the common information that can help us explain all observations. But for saturated model, we don't have that. There's no common beta. So that is the biggest difference. So if you think about a saturated model, how would you fit the model or estimate each mu I? you only have one observation yi, right? Then if you just want to maximize the likelihood based on this normal distribution, you would just estimate mu I hat as yi, right? That will be your best guess. So in this case, MLE, maximum likelihood estimation, mu I hat is just yi. So yeah, you just use the observation as the parameter estimate. But something maybe I will just briefly say here, there's a very, very interesting theoretical result. It's called Stein's dilemma. So by previously very renowned statistician Charles Stein at Stanford. So in the Stein dilemma, basically it says that even though MLE is this, but if you want to use a different criterion, that is, if you want to minimize the total mean squared error between the mu I hats and yi's, then the best estimate for each mu I is not yi, but you need to shrink it towards zero in somewhat. And that is called the James Stein estimator. So that is like the original idea of shrinkage, where it came from. But for now, we're not talking about that, because here we focus on MLE. But for MLE, it is this one. But it can become counterintuitive that MLE doesn't give you the smallest mean squared error. The reason is because even though you are unbiased, so this is an unbiased estimator for the true mu I, but because you have too many parameters, and each estimate based on only one observation is very unstable, has large variance. So therefore, mean square error is a combination of bias square and variance. So therefore, you would sacrifice your unbiasedness by adding bias, but to decrease your variance. Then you're doing better in MSE. So that is the intuition there. But yeah, it's a very interesting stories. But so far here, we'll just say that using MLE, mu I hat is yi. So we have the baseline model, saturated model to define two extremes where the predictors are not there. But for linear model, it's in the middle. We are trying to use our P-1 predictors to tie our mu i's in some way using the linear model. Okay, so what ANOVA does, I said it's a decomposition of variance, right? But another way to interpret it is basically comparing linear model with null model. So in the basic form of ANOVA, what we are doing is we basically compare this linear model to the baseline null model to see whether it can significantly better explain the variance in our yi. Yeah, that's it. So basically, this is a typical ANOVA table. I'll write it out. So it has the following columns. The first column is called source of variation, short as SV. And the second column is called sum of squares, SS. And the third one is called degrees of freedom, degree of freedom. And finally is the mean squares. And it is MS. Okay, so these are the columns we need to do the ANOVA. Oh, and finally, I think I should have one more column here is the F statistic, but we can do that later. So this table is something we can calculate based on our data. And so in terms of SV, source of variation, we consider the regression, which is what our model can explain about the variation in Y, residual, and total. So if I put what we calculate in the ANOVA equation, which is this SST equals SSR plus SSV, then this is SSR, this is SSE, and they add up. They add up to SST. Okay. Yes. Yep, they add up to SST. So this is the first column. And for degrees of freedom, this is very important. So it's related to the formula here. What is the degrees of freedom in SST? This is something we said last time or the time before. That is, if we are talking about variance, we lose 1 degree of freedom because we don't care where the average is. We can rather shift the average but maintaining the same variance. And in other words, when we calculate the variance, we will calculate the average. We're basically losing 1 degree of freedom because it's just like around this average, how my y1 to yn are different from the average. But if I add one thing, add a constant to every yi, this variance will stay the same. So this SST has degrees of freedom n-1. And that is also the denominator we use in our unbiased estimate, right? Okay, how about residual? Residual, we said, is this degrees of freedom is n minus p. And that is the variance formula sigma squared hat we use as unbiased estimator. It's n minus p. That's something we derived before. And the regression is their difference. N minus 1 minus n minus p. It's p minus 1. Okay, what does this mean? This means that we are introducing p minus 1 predictors because we have just one intercept in the null model that we are adding p minus 1 predictors to make beta p-dimensional. Okay, then with this, we can easily do the calculation for mean squares. So MSR, mean squared regression, is just defined as SS over its corresponding TF. So it is SSR over p minus 1. And this is called MSE, mean squared error, and it's actually SSE divided by n minus p. Okay, and the F statistic, finally, the column F statistic is just to compare these two. Basically, the goal is to check that we have, how to say, we want to compare MSR to MSE. We want this ratio to be large, right? Because we want the majority of the variance in my y to be explained by the regression rather than by the residual. Otherwise, it means the model is not informative. It doesn't tell us much. So this is the F statistic, okay? And you can just do the calculation. Basically, it's SSR over p minus 1. That's your numerator. SSE over n minus p. That's your denominator. And recall our likelihood ratio test. Let me just grab that piece of paper from last time. The likelihood ratio test is very similar. So basically here, RSS over n minus p in our current term is SSE over n minus p, same denominator. Over here, SSE under the null model minus SSE under the full model, which is what? Which is exactly our SSR. Because basically this is, let me see, this is exactly our SSR because RSS under the null model is essentially this SST. And RSS under the full model is SSE, and their difference is SSR. That's it. And one more thing I want to say is here you would need to divide the numerator by p minus 1, SSR p minus 1. This is just SSR. Okay, so what is the difference here is that in the F statistic, if you want to go with the likelihood ratio test statistic to F, you need to further divide by p minus 1. Okay, and p minus 1 is actually here my p2. Sorry about this difference in notation, but p2 is the subvector we're testing to be 0 now. So in our case, p2 is p minus 1 because we're looking at all the predictors together. So this is also something very interesting, which is a relationship between F distribution and chi-square distribution. So regarding ANOVA, coming back here, under the null hypothesis, it follows an F distribution, all right? And its degrees of freedoms are already provided. P minus 1 as the numerator degrees of freedom, n minus p as the denominator degrees of freedom. So this is the F distribution. This is a chi-square distribution. And let me try to summarize what I just said. I'm saying is that if you go back to the likelihood ratio test, you are basically having it using our term here, SSR over SSE divided by n minus p. Okay, and this happens to be just p minus 1 times my F statistic. Okay, and this one I would say follows chi-square distribution with p minus 1, with p minus 1 degrees of freedom. Okay, and this is what? This is exactly the asymptotic distribution of F. So basically I'm saying that if F follows F distribution with p minus 1 and minus p degrees of freedom, then what I can do is that I multiply p minus 1 to F, p minus 1 times F. This will converge in distribution to chi-square p minus 1 as n goes to infinity. So when this n goes to infinity, then the asymptotic distribution is chi-square. So there is such a relationship between F distribution and chi-square distribution, similar to T distribution, between T distribution and normal distribution, standard normal distribution. So, but this is just going to see the connection between the two. And basically for likelihood ratio test, this thing under the null, this is called asymptotic null distribution, okay? But in the ANOVA, under the assumption that the errors are normal distributed, IIDE, common variance sigma square, under that simple assumption, then this F distribution is exact. It's not asymptotic. Okay, but there's a connection between the two. I'll pause here for a moment and let you ask questions if you think anything is confusing. I would say one confusing part is SSE and RSS are the same thing. So basically, what I'm trying to write here is to translate this to this in the ANOVA language.
This may be a silly question. I maybe just missed this, but when we're sort of reading off an ANOVA table or something,
Yeah.
how do we actually know whether or not the additional information that the predictor help us get is significantly different?
Oh, no, you would just use the F test statistic and convert that to your p-value and use the p-value to decide. Basically, in this very basic form of ANOVA table, it is about whether all p minus 1 predictors have any effect, jointly have any effects. If you reject this test, or if you have a very small p-value, if you use the F calculation based on table, put it into the F distribution, look at the right tail probability and see whether it is small, right? If that's your p-value. If it's 0.05 and less, you would say, I think my regression model is informative. That is, it's better than the baseline or null model. That's how you read it. But this is the basic form of ANOVA. Now we're going to talk about our more, how to say, practical form. And this is what you will get in your R output if you use R for data analysis. So this is called hierarchical ANOVA. So in this case, it's like the problem we tackle with the wall test. That is, we're comparing two models, one with a subset, only a subset of predictors. So two linear models. So basically, we have, if our design matrix written as two columns two column submatrices stacked together, x1, x2. So x2 means the predictors that are additional, whether you want to include them or not. So in this case, my two models are the full model is I just write the matrix form, y equals x beta plus epsilon. Okay. And versus if I use the reduced model, just the covariance in x1 only. I can write y equals x1 beta 1 plus epsilon. So these are the two models we compare. In other words, we try to answer whether the predictors, additional covariance or predictors in x2 are informative, are useful for our prediction. Okay. And so basically, what do we do in this case? If we still write this ANOVA table, let me put it. SV, source of variation, SS, DF, MS, and finally F statistic. If I do it this way, then here are the sources and the source for regression. Like we previously just have one SSR, right? The regression can be further decomposed into the source of variation that can be explained by X1 only in the reduced model, and the additional explanation from X2. So therefore, in such a ANOVA table, we will have a row called X1 and a row called X2 given X1. This is the additional predictors and residual. What this residual means, what the full model cannot explain. Okay, and then finally total. All right, so when we just have S1 as the predictors only, our SS sum of square would just be called SSR1, which is what? Which is based on SSR, just going back here. So SSR, going back here, is what we compare between the fitted predicted values y hat and y bar. So in this case, if you say SSR1, it is based on the predicted values of the reduced model. Okay, so you will use that to basically get your y hat and then compare to that y bar. So I will just write here y hat minus y bar squared, but this comes from the reduced model by fitting that, not the full model. This is SSR1. And as to x2 given x1, the additional explanation by x2, by the predictors in x2, this is actually SSR1, 2 minus SSR1. So by saying SSR1, 2, we're talking about a full model. So we're using a full model to calculate SSR. And because we know the full model should explain more variation than the reduced model, then SSR1, 2 should be bigger, or at least bigger or equal than SSR1, right? So this should be non-negative. And finally, residual. Residual here is SSE1, 2. That is, we use the full model to get the residuals and do the SSE calculation. Okay, and now the degrees of freedom. So the total is still SST. So I put it here, total variation. And we can actually show that because you see, basically, when you add up the first two rows, it becomes SSR1, 2. So just under the full model SSR, because SSR1, 1 is canceled here. And we know SSR1, 2 plus SSE1, 2 is SST, right? Under the full model, we have the decomposition. This is the same as the basic form of ANOVA we just introduced. Now, degrees of freedom. Maybe I'll just move a little bit here. This is trickier. We know SST is n minus 1. And again, we know what is residual n minus p. Probably I should say that, be more general, this is p1 dimensional, p2 dimensional, okay? And p1 plus p2 equals to p. Okay, that's n minus p. And then what is x1? X1 is just the additional predictors we included besides the intercept, right? So that's how we do better than baseline model. So this is actually P1 minus 1. Okay. And this one should be what? P2. because we are including additional P2 predictors into the full model. And we have P1 minus 1 because we are excluding the intercept. Okay, and then we will do the calculation correspondingly. MSR1 is just SSR1 divided by P1 minus 1. Okay, and MSR2 given 1, I'm writing 2 given 1, is just SSR12 minus SSR1 over P2. And MSE12 is just SSE12 over M minus P. Okay, finally, in the previous ANOVA table, we're comparing MSR to MSE to get F statistic. Here, to answer this hierarchical question, that is whether or not our X2 predictors make any difference, then this F statistic would be defined as MSR2 given 1 over MSE12. Okay, and here the null hypothesis is that the coefficient of X2 in the full model. So if we just write out the full model as some part explained by X1, like X1 times its beta 1 plus X2 times beta 2, because we can do that with the matrix calculation, matrix multiplication. So then we are saying basically the coefficient of X2 only is 0. Under this null hypothesis, the F distribution would have degrees of freedom as P2 and minus P. And you are going to compare your F statistic with this null distribution and call that right tail as p-value. What's the intuition behind this approach? Here, the intuition is that you are comparing this additional variance explained by X2 to what the residual explains. And you want this additional explanation to be bigger than the residual, right? Than the variance in the residual. Otherwise, it's hard to say the X2 predictors really can be explanatory. So the residual variance in the denominator MSE12 is basically a baseline. It's used as a reference, and we're comparing the MSR explained by additional predictors to that. That's it. So this is hierarchical ANOVA, and I want to say that even though we can write out MSR1, but to my knowledge, we don't use it, actually. We won't use it in any way. It's just here, where what we really care about is just the MSR2 given 1. That's more important, because this question is about what additional contribution can we make by including additional covariates or additional predictors. Okay, so this one you can totally ignore it because we're not using it in any way to my knowledge. Okay, any questions regarding this? Regarding R implementation, this is something I can say. If you want to get the ANOVA table out of R, this is the command, which you can do in multiple ways. I think you can do it like summary function called on a linear model object. LM is the function for doing linear regression. Or you can say Y, this means regress on X1 plus X2. Okay, and you will get a summary on hierarchical ANOVA table like what we have here. So X1 appears on the top, X2 given X1 next. And then in this case, using this ANOVA, the question is about whether X2 makes significant additional contribution. But it's not the same as if you swap the order. So if you write it this way, X2 plus X1, you swap the order of X1, X2, it will be different because this is answering a different question. That is, I put X2 into my model first, and then given X2, I want to know whether X1 has any additional contribution. So in this case, this is something to keep in mind. It has a different order of models, which is your first model. Here it's just X1 only. and then you add x2. While in the bottom, you first have a model with x2 only, and then you add x1. So in other words, this ANOVA will help you detect the effects of x1 in this full model, while the first one will detect the effects of x2 in the full model. So we should use that carefully. Okay. And one more thing I want to say is R squared. Okay, besides the F statistic ANOVA, R squared is commonly used as a metric. Okay, R squared is called coefficient of determination. So it is just SSR over SST. So out of my total variation in Y, what percentage can be explained by my model? Okay, and you can also write it as 1 minus SSE over SST because of the relationship. But one thing to note is that if you're under a simple linear model, okay, simple linear model with one predictor, X, so just one predictor, then R squared turns out just to be the square of the Pearson correlation between Y and X. The two vectors, you have an observed vector of Y, Y1 to Yn, you have an observed vector of this predictor, X1 to Xn. If you calculate their Pearson correlation and square it, it turns out to be just equal to this R squared, which is a very nice property to know as well. Because we know that for linear regression, right, if you treat, since we have only one predictor, you may wonder whether I can swap the predictor and Y by treating predictor as X, X as Y, and then Y as X. If I do that, would that be good? So I would say for ordinary D squared, you can show that, just grab another paper. So for the simple predictor scenario, simple linear regression with one predictor, X, right? We can consider two ways, Y on X, X on Y. So one thing we can say is that they are not identical in terms of the parameter estimate. Why is that? So basically, you can write it, if I just write it as yi equals to beta 0 plus beta 1 xi plus epsilon I. Okay, this is one linear model. The other one is I can write xi as, I'll just say different parameters, gamma 0 plus gamma 1, yi plus probably eta I or something I. Yeah, the error term. And then you can see that fitting each model using ordinary least squares. Okay, I can give you the result. This is more like an undergraduate material. The result is that beta 1 hat, OLS here, is the coefficient correlation between X and Y. So let me just call R as the correlation, Pearson correlation between the two vectors Y and X. So beta 1 is known to be Pearson correlation divided by standard deviation of Y over standard deviation of X. This is what we get from this direction. For the other direction, gamma 1 hat is R, also same Pearson correlation because it is symmetric between X and Y. I can swap them, X and Y, and get the same R, divided by SDX over SDY. So then you can see that in the ordinary least square, even though we hope to have the two parameters beta 1 and gamma 1 to be reciprocals, right? We hope to have that because one is effect on xi, one is effect on y. If we just do mathematics, not statistics, we can divide beta 1 to the sides and we can have the reciprocal relationship. But beta 1 hat is not the reciprocal of gamma 1 hat. You can say that because of the existence of the correlation here. So that is a very well-known fact. But if you want to have this relationship hold, right, the two slopes are reciprocals of each other, there is something alternative to ordinary least square that is called major axis regression. So some people call it MA regression. So the MA regression will guarantee that the two lines you fit here, so the two lines you fit either way, so the two regression lines are symmetric about this y equals x diagonal line. So that is what you can get from the major axis regression. So basically, you can satisfy this beta 1, gamma 1 reciprocal relationship if you want to do that instead of using the ordinary square. But the major axis regression has a very different objective function or loss function for finding beta 1 and gamma 1 for finding the coefficients. So what it does is that with basically when you have dots here and when it fits a line, it's not minimizing the vertical distances, but minimizing the perpendicular distances between every dot to the line. So that's its different objective. It's not a vertical distance. So that's why in its treatment of the two variables x and y, they are treated as symmetric. While in the ordinary least square, we're not treating y and x symmetric. We're thinking of x as the predictor, y as the response. And we want to predict the response as accurately as possible in terms of vertical residuals. That's it. Okay. And one more thing I want to say is about the interpretation of a linear model, because we're trying to wrap up this part about the model interpretability. And ANOVA wall test, likelihood ratio test are all about inference of some subvector beta, which is helping us to decide whether these predictors have any effects, right? That's the reason why we're doing this. But how do we interpret such coefficients? That's my second question. So if I have these two models, yi equals to beta 0 plus beta 1 x1 I, let me think. Yeah, maybe I'll just use the vector form. Sorry, all right. Again, using my notation x, x1, x2. Okay, so the intercept is in x1. So I'll write yi equals to xi transpose, x1 I transpose beta 1. So for x1, I'll just call the rows as x1 I transpose. Okay, I from 1 to n. And for x2, I'll write the rows as x2 I transpose, I also from 1 to n. Okay, so this is the first model, epsilon I. I just have my design matrix x1 versus second model, x1I transpose, I'll now call it beta 1 prime plus x2I transpose beta 2 prime plus some epsilon I prime. So now I'm trying to intentionally differentiate the two models by not using the same beta 1, not the same epsilon I, to mean they're different, two different models. And my question for you to think about is my beta 1 and beta 1 prime the same parameters for interpretation? This is very crucial in a linear model, in this so-called multivariate linear model, because we have many predictors together. So my answer to you is that beta 1 is not equal to beta 1 prime, and they cannot be interpreted the same way, which is actually a confusing part of linear model. That is, how do we interpret a beta 1 prime or the effects of my predictors in x1 depend on what else I include. So by including more predictors, the interpretation will change. So the reason is that in such a multivariate linear model, we are talking about conditional effects. So any effects we have in the beta coefficients conditional on other predictors. We're not looking at one predictor alone. So therefore, we can call these, some people call them conditional effects, or you cannot say it's the effect if we only have x1 alone. So I think we'll stop here and we will hopefully get back to this later. But just to give you the first impression that it is not the same interpretation. So basically having additional covariates or predictors will change your interpretation of the existing predictors coefficients. Okay, so I'm still debating whether I will post the homework one today or we'll wait until next week. I can stop sharing this because the reason is that we are still waiting for the approval from the university regarding the grading, like the spatial reader. So because we cannot ask our graduate student to work on the grading before we have the approval. That is the hard constraint, but we'll see. So I'll make a decision to whether post it and give you a longer time for submission, or we'll do it next week. Yeah, but I know for Monday it will be a holiday, right? So Monday will be a holiday, so there won't be any classes on that day. But on Wednesday, what I plan to do, because I unfortunately won't be in town, I will record a lecture. And I think it will be something related to what we discussed, but it's more from my recent research. Hopefully we can share another aspect with you. And what I will do is that I will ask my postdoc to be there in person if we return to in-person teaching and answer your questions. So the recording itself will be about 1 hour. That's my plan. And there will be a Q&A. And also I'll be happy to answer your questions on that when I return, so or at our office hours. So that's the plan for next week. And then we will return to our regular class material. So the recording I plan to do will also about linear model. So hopefully it can share with you some numerical perspective of how do we tackle the problems we have discussed in the class. All right, so thank you. Then just let me know if you have any questions, and hopefully I can see you in person very soon. Hopefully the situation will be improved. Okay, bye everyone.
Thank you.
Bye, thank you.
Thank you.
Thank you, bye.